Hello everyone, myself Bhupesh Kumar. I am currently working as a researcher at the University of St Andrews. First, I would like to thank the conference organizers for the opportunity to present my research. Today I will be discussing my work on impact of non-hermiticity and nonlinear interactions on the disorder-induced localized modes in random laser. In this talk, I will focus on non-Hermitian photonics, where introducing gain and loss leads to complex non-orthogonal modes. This framework allows us to explore new way of controlling light, especially in open disorder system. A key phenomena such as Anderson localization, where strong disorder can confine light into small regions. There are several unanswered questions in the context of localization and non-Hermitian physics. Few of them are like how do gain and loss affect these localized modes? Do the lasing modes correspond to the underlying passive modes? Are these modes are robust under no linear effect like gain saturation mode competition? We have tried to answer all these questions in this work. Anderson localization is a universal phenomena in which propagation of wave is suppressed due to disorder in the gain medium. It was originally predicted for electron moving through the crystal with random impurities. But this concept applies to any type of wave, including light wave or photons in optically disordered material. When the disorder is very strong, light waves undergoes multiple scattering, and the scattering wave interferes with each other. This interference can be both constructive and destructive, which prevent waves from spreading through the scattering medium. As a result of this, wave becomes effectively trapped in the confined region and forming a localized mode. The key condition to observe Anderson localization is scattering has to be very strong. It has to be strong enough such that scattering mean free path is of the order of the wavelength of the light. Non-Hermitian photonics and its connection with Anderson localization. Non-Hermitian photonics introduce gain and loss and leakage in a open system or it is an open disorder system, which leads to complex eigenvalues and non-orthogonal modes. This framework extends our ability to control light in open and disorder system where Anderson localization can arise due to strong disorder, confining light to exponentially localized state. Traditionally studied in Hermitian models, but gain and loss can reshape or destabilize these localized modes. Here random laser serve as a natural platform where non-Hermitian effect and localization can be investigated together, which enable us the exploration of new regime of wave transport in light-matter interaction. In this work, we use random laser as a platform to investigate the impact of non-hermiticity and non-linearity on Anderson localized modes. First, I will briefly explain how random lasers are different from conventional laser. So here a conventional laser, we know that it consists of two parallel mirrors placed around a gain medium. One mirror is fully reflected, other is partially reflected, which allow laser beam to exit. In this system, laser light waves are reflected back and forth between the mirror, causing constructive interference. Only specific wavelengths that satisfy the resonance condition of the cavity are amplified. On the other side, random lasers, there is no traditional optical cavity like a conventional lasers, but it has lots of randomly distributed scatter inside a gain medium. So when optically pumped, multiple scattering of light take place inside this disorder gain medium, and necessary feedback is provided, which provide the necessary feedback for amplification and lasing. So here lasing is expected when the gain overcome the losses. Since the gain is proportional to active volume, here the losses result from leakage out of the surface of this volume, and there must be a critical volume where threshold is reached. The random lasers are therefore a mirrorless lasers, and they have been studied in different type of scattering medium. Random lasing has been demonstrated in several platforms. Micro random lasers were introduced as a way to overcome the difficulty of fabricating highly reflective mirrors at microscopic scales, allowing light confinement and lasing through multiple scattering. A widely studied material, zinc oxide, which emits strongly in ultraviolet, a special region where mirror fabrication is particularly challenging. In this context, mirrorless random laser based on zinc oxide have emerged as an effective alternative, and this has been investigated in both 2D and 3D disorder system. Cold atom gas provide another clean and tunable system where ongoing research focus on gain mechanism and interplay between disorder and random lasing. Similarly, opals and photonic glasses infiltrated with dyes have been used to demonstrate disorder-induced lasing. The photonic crystal with intrinsic disorder introduced while fabrication has been used for random lasing. Imperfection, which were considered a drawback in photonic crystal, now can be seen as a resource that can be exploited for novel lasing behavior. Random laser faces several intrinsic challenges. Their emission spectrum is largely unpredictable and highly sensitive to the microscopic changes in the disorder system. Even a small perturbation can cause extreme variation in lasing behavior. Unlike conventional laser, random laser exhibit low spatial coherence, resulting in non-directional emission. Due to highly non-Hermitian nature, lasing threshold is typically high, and non-linear effects such as spatial hole burning and mode competition further complicate the mode dynamics. Finally, due to significant spatial mode overlap, it is generally impossible to pre-select or control which mode will laze, and which limits the spectral selectivity in random laser. In the next slide, I will discuss how researchers have used different methods to control the emission from random laser. This slide shows three main approaches to control lasing emissions. First, designing the disorder. By introducing controlled randomness in the material, we can influence how light scatter and tailor the lasing spectrum. Second, optimizing the photonic structure. Instead of random disorder, engineered photonic crystal or band tail structure can confine light and give us more predictable emission spectrum. Third is designing an optical gain. By shaping the spatial distribution of gain or using selective pumping, we can decide which modes are amplified and control the output spectrum. So overall, laser emission can be controlled by tuning disorder, or by carefully engineering photonic structure, or by selectively designing the gain. We have designed and fabricated our own 1D disorder gain medium using nanofabrication technique. A passive polymer host, which is PMMA, which is also called polymethyl methacrylate, with a molecular weight of 49,500, is doped at a concentration of 5% weight with the commercial laser dye DCM. Once the solution is prepared, a 600 nanometer layer of this solution is deposited by spin coating at 1000 rpm for 60 seconds on a fused silica wafer, and we later solidify it by baking it at 120 degrees Celsius for 2 hours in an oven. To fabricate 1D disorder samples, 125 randomly distributed parallel grooves, each 200 nanometer wide and 50 micrometer long, covering a total length of 1000 micron, were carved onto the PMMA DCM layer using E-beam lithography. Here you can see SCM images of the air grooves separated by an on average distance of 8 micron on a PMMA DCM layer. A laser strip which matches the dimensions of the sample from a frequency doubled ND arc laser operating at 532 nanometer is used to uniformly pump the random structure. Once the laser or optical pump energy exceeds the threshold, a sharp discrete peaks appears on a broad emission spectrum, which make this laser a multi-mode random laser. But to achieve a single mode emission, we have used a feedback-based iterative pump optimization method, which I will explain in the next slide. To achieve single mode operation in this random laser at various desired wavelengths selected from the uniform pump spectrum. This we have achieved by iteratively shaping the optical pump selectively to selectively excite the individual modes. To achieve that, this the pump intensity profile is tailored using a computer-controlled spatial light modulator which modulates the beam before projecting it onto the backside of the sample. After approximately 200 iterations, the optimization algorithm converges to a non-uniform pump profile, you can see that here, that enhance the target lasing modes while suppressing other modes below the threshold. This figure illustrates 5 different pump profiles. Each corresponds to a unique lasing wavelength, confirming the tunability and effectiveness of this approach. We have used Nelder-Med simplex method for optimization. This slide focuses on the concept of localization in random lasing. On the left, you see an experiment setup where we use a laser pump shaped by a spatial light modulator and the beam expander to excite the disorder sample. The emitted light is controlled by the camera, is collected by the camera. Because of scattering from the grooves inside the sample, we can directly observe spatial profile of the lasing modes. On the top right, this image shows how lasing emission is not uniform across the sample, but instead appears in localized spots. This is the signature of mode localization caused by underlying disorder. The graph at the bottom right shows both spectral and spatial signature of these modes. Panel A to G, each mode appears as a sharp spectral peak within the visible range around 595 to 615 nanometer. Correspondingly, panel H to N shows each of these modes is spatially confined to a small region of the sample rather than expanding across the entire system. This method actually acts as an eigensolver, which allows us to retrieve the non-Hermitian eigenmode of the disorder system. This provides a direct link between the experimental observation and theoretical modeling. Now I will discuss the robustness of the Anderson localized mode to the selective pump profile. First, on the left panel of this figure, we see different pump patterns on the top obtained by running 3 different iterative optimization on the same target mode. The panel A to C shows the same wavelength and the corresponding spatial distribution in the panel D to F, which are identical, then confirm that despite changing the way we pump the system, the emission converge to the same localized lasing state. This demonstrates the intrinsic robustness of the mode selection in such a disorder system. Second, robustness is not just limited to pumping condition. As shown in this bottom right plot, we fabricate this spectrum is obtained after fabricating 3 different samples with the same disorder configuration, and when pumping uniformly, they emit entirely identical spectrum. This reproducibility is remarkable because this means that random laser, despite their name, can produce highly consistent result when the disorder is controlled. Overall, the key takeaway is that random lasing is not entirely unpredictable. The localized modes are robust against variation in the pump pattern and can even be reproduced across different samples, making them reliable for practical application. To test whether localized modes or of the disorder system corresponds to passive lasing modes or not, we optimize the pump to excite a single mode lasing at 600.20 nanometer, and its spatial profile is localized at the center of the sample. Even when the pump area was reduced, you can see on the top here where the pump area is reduced to a small section, the same wavelength was excited and the spatial profile remained similar, almost similar, with a correlation of about 82%. And when we add a weak uniform pump to the whole profile, which compensate for the losses, we recovered almost the same identical profile as in case of, you can see, as compared to the panel A. which confirm that these localized modes are in the center of the sample are highly robust. However, the modes near the sample edge, where non-hermiticity plays a very stronger role due to the higher losses or leakage, we observed a deviation. Lasing mode selected at 605.21 nanometer shifted in spatial structure with much lower correlation than that confirms the edge modes are modified by gain and losses or by higher losses. In summary, localized mode replicate passive mode in the bulk because of lower losses, but near the boundaries of the non-Hermitian effect are significantly higher, and that actually modify them. Over localized random laser can be operated in either single mode or multi-mode regime, as I have explained in previous slides, making it a very powerful system to investigate interplay between localization and nonlinear effects such as nonlinear gain, gain saturation, mode competition aspect that have not been thoroughly studied. So to investigate that, uh, first we pump the sample uniformly, covering its whole area, and we observed lasing action at 80 nanojoule, where sharp discrete peaks appear in the emission spectrum. And importantly, the multimode spectrum remains stable as we increase the pump energy further and further up to the gain saturation. I mean, just up to the point where we don't see any increase in the intensity of the lasing modes. And we observed there was no sign of energy pooling across the lasing wavelength, which indicates that underlying or the study, investigated the modes which we are investigating, uh, the localized modes are very robust against the non-linear effect even in multimode regime. In this figure you can see that the wavelength of the modes, the lasing wavelength remains same by these vertical points as we increase the energy of the pump. In our second experiment, we investigate how nonlinear gain and gain saturation affect a single localized mode. For that, we select a single lasing mode at 603.10 nanometer localized near the center of the sample and applied a very narrow pump strip of about 10 micron to excite this mode. The pump energy was increased stepwise from just above threshold at 14 nanojoule up to 147, where saturation the gain saturation starts, and we even go further up to 200 nanojoule, and we found that even after pumping with so much energy, the peak intensity of the mode increased by more than 3 order of magnitude, and its spatial profile remained perfectly preserved. The correlation between and low energy and saturated energy profile was about 97%, and this shows a clear evidence that localized modes are remarkably robust and they are insensitive to nonlinear gain and remain stable even under strong gain saturation. In this work, we show that non-Hermitian photonics and disorder leads to localized modes in random laser, where central lasing modes closely matches the passive modes of the system and spatial profile is highly preserved with much higher correlations. And on the other side, the edge modes which are affected by non-hermicity and losses showing altered profile which can be restored but partially with the loss compensation but not fully recovered, so correlation is very less. And the final thing is the localized modes are robust to non-linear effect, which includes gain saturation mode competition. That's it. Thank you. If you have any question, just feel free to ask me. My email address is given in the first slide.